Okay, thanks. I wanted to go into a couple of things on acids. So writing out acid dissociation reactions. So we want to be able to do this for strong acids and weak acids. The idea is the same as what we've been doing before, so we're just going to give it a slightly different name. So acid dissociation reaction. I'm going to start with something. In this case, I'm going to start with hydrochloric acid, HCl. I'm going to always assume that these are in water, so it's really helpful to write water there. I'm going to ask you to do that for these because that's really helpful and prevents a little bit of confusion later. So the key thing about hydrochloric acid, so a very strong acid, that means it's going to dissociate entirely, right? So every single hydrogen bound to a chlorine that you put into the water is going to dissociate, and I'll have, in this case, hydronium ions. Sometimes you take a shortcut and write it as H+. So I'll have hydronium ions floating around and chlorine ions floating around. So these are two things that I want to show. I want to show having my hydronium ions and my chlorine ions floating around. So this is the acid dissociation reaction. I'm going to write equilibrium constant for this, and I'm going to do it the same way that we've written all the other equilibrium constants. I'm going to take K, I'm going to have roughly products over reactants, the concentrations of each of those. So in my products, well, it's going to be my concentration of H3O plus times the concentration of Cl minus, and I'm going to divide this by the concentration of HCl. Because water's a liquid, remember, I'm going to leave liquids and solids off my equilibrium expressions, and this is really because we have a huge amount of water floating around, so if we use a little bit of it or not, it really makes no difference. So the concentration doesn't change, and to get an equilibrium that makes sense out of this. So in this case, I expect this to entirely dissociate. So I'm going to end up having a lot of product and very little reactants. So I'm going to have a K value, which is going to be very large. So this is going to be much greater than 1. So, and this is for a strong acid. So I can do this for any strong acid. Right? So I can take another strong acid. Let's take HNO3, nitric acid. This is going to be aqueous. I'm going to combine it with water, which is a liquid. This is going to be an equilibrium. I'm going to get out of this my hydronium ion plus whatever is left over. Remember, I'm just transferring one hydrogen. So I'll have my nitrate polyatomic ion left over as well. When I write my equilibrium constant, this is going to be roughly products over reactants. And I'm going to have this as being the concentration of H3O plus times NO3 minus divided by the concentration of HNO3. Remember, I'm going to leave water off because it's a liquid. This is a strong acid, so I'm going to have a lot more products. It's going to dissociate almost entirely, so I'm going to have a lot of products, very little reactants. So my K value is going to be much greater than 1. So in chemistry, this is a way of writing equilibrium expression. Because it's an acid, I'm going to give it the value of Ka. So it's the same thing, equilibrium constant, but it's just an acid, and now has this value. So hopefully you remember reading these, that this is telling me the molar concentration of hydronium ions times the molar concentration of nitrate ions divided by the molar concentration of the conjugated HNO3. So this is my acid that's stuck together, so that hydrogen is adjacent to the nitrogen. Okay, strong ones, they dissociate entirely. Sometimes we'll write it with a one-way arrow instead of an equilibrium, because it dissociates entirely. So it's not really an equilibrium, and all of this gets converted into that. So pretty common for us to write strong acids with a one-way arrow and not an equilibrium. But in this class, I'll ask you to write this as an equilibrium, so we can put in the double arrows to represent that. Okay, let me go into a couple other. So let's go into weak acids. So weak acids. Let's look at this case in acetic acid. So really common weak acid to take a look at for these sorts of things. And this is another view of a weak acid. So I'm going to look at this as a ball and stick model. So acetic acid, so this is HC2O2 H3. Oh, I got to write this one down. So it's gonna look like this. So this is showing me my oxygens in red. I have 2 oxygens. This is showing my 2 carbons in black, and then my hydrogens are in white, and the one that's going to come off is shown here in green. Right. So this is my conjugated acetic acid. So this is what we mean by the acid that's conjugated. It's all stuck together. So the hydrogen is still on the acid. This hydrogen is going to move to this water. And then you can see this green hydrogen now shows up in this hydronium ion. So my oxygen and water now has 3 hydrogens coming off of it. And it comes off of this this pair of oxygens that's stuck on my acetic acid. So we're going to represent this as an equilibrium. Again, it's a weak acid, so more valid to use equilibrium arrows to show this. So I'm going to write my acetic acid is HC2H3O2, one of several ways to write this. And this is going to be aqueous. I'm going to combine this with water, which is a liquid. And this is an equilibrium. And I'm going to get out of this H3O plus and my acetate polyatomic ion. So these are the two that I'm going to get out. So what is my equilibrium going to be? Well, the same thing we've been doing for equilibrium. I'm going to take K. I'm going to take roughly the concentration of my products over my reactants. It's going to be the concentration of H3O plus times concentration of C2H3O2 minus. And I'm going to divide this by the concentration of my conjugated acid, right? All stuck together. I'm leaving water off because it's a liquid. This is a weak acid, so that means I'm going to have few products and mostly reactants, right? So this value for K is going to be much less than 1. And because it's chemistry, I'll call this Ka to represent an acid dissociation reaction. Let's do one more acid. So let's look at HF. So HF, very weak acid. So notice that the fluorine is a halogen. My other halogens, chlorine, bromine, iodine, those are all make very strong acids when I put them with the hydrogen. It turns out that fluorine, when I stick a hydrogen on there, it gets stuck together pretty good and doesn't come off. So it's a weak acid. It doesn't like to dissociate, but it can. So I'm going to combine this with water. Again, I'm always in aqueous. My acids are always going to be in aqueous solutions. So I'm going to assume there's a bunch of water around there, which is a liquid. This is going to be an equilibrium because it's a weak acid. And I'm going to be generating my hydronium ion, as I do with acids, and my fluorine ion. I can write equilibrium expression for this. K, I'll call this Ka because this is acid dissociation, which is going to be roughly the products over the reactants. And this is going to be H3O plus times fluorine minus, all divided by concentration of my conjugated acid. Can you predict if the K value is going to be large or small? Right, so it's a weak acid, so it's going to be a small K value. And this one is extremely small because this just doesn't dissociate very much. The fluorine is very good at holding onto that hydrogen. So briefly, let me mention bases. So we're going to do this. We could do the same thing with bases. We're not going to go into it too much, but we could do the same thing with bases. Remember, my acid is a proton donor. My base is a proton acceptor. So let's take a base, right? So take ammonia, NH3. And hey, this is going to be aqueous. So household cleaner, ammonia. I dissolve this in some water, and I get this reaction that happens, right? So this is a base, right? So my base is going to accept the hydrogen. The hydrogen is coming from the water. So I'm going to be left with NH4 plus and OH minus. The water lost the hydrogen, and now it's a hydroxide. So this is a base reaction, right? We can write equilibrium for it. So this is K, because it's a base, I'll put a B there, why not? So this is a base dissociation. So this is going to be, again, same idea, my products over my reactants. And in this case, I'm going to have NH4. If I could write this, I'm going to have NH4. Oh, NH4 plus. Okay, grief. Times OH minus. And I'm going to divide this by the concentration of NH3. Notice I'm leaving the water out of it, as I always do. All right, so the same idea. So my products over my reactants, if you can write them correctly, which I seem to have trouble with in this one, that you end up with now a base dissociation reaction. So if this is a weak base, this is a weak base that I'm going to have more reactants, so my values can be less than 1. If it's a strong base, I'm going to get a lot of hydroxides, and my value is going to be greater than 1. So bases and hydroxides go together pretty well. So if you see a hydroxide being generated, that you can have confidence that that's going to be a base and easier to identify. Anyway, I hope it's helpful. So you should be able to write out the acid dissociation and if necessary base dissociation reactions, but primarily we're going to focus on acid dissociation reactions because those are more interesting to us. If you have any questions, let me know. Thank you. Bye.